let's go ahead and get started. Okay, let's go ahead and get started. I know you guys are excited about Valentine's Day tomorrow, but let's go ahead and get started first. Okay, so you still have your homework assignment due next Tuesday. That's the joint homework assignment. I suspect many of you have at least started on that one or done already. Okay, I haven't really checked how many people have turned it in already, but I know several people are done with it already. So what we'll do today is, last time we were pretty much done with the discussion of the memory bus, but I found where I put all my notes regarding the memory cycles. So that's the first thing I will do is to point you to that document, so that way you can you know where to find that stuff. So if I remember correctly, it is in something that is obvious, memory access. Try that, right? And in the document, it has a section that says memory cycles. So it has, everything is kind of written down, but it's the same thing that we talked about last week. Okay, it's basically the same content. It's just written down, and you can actually see the details. The other thing I want to show you guys, at least some of you who will become computer engineers or electrical engineers, this is something that you have to encounter, you have to deal with when you get into the profession of becoming an electrical engineer or a computer engineer, or anyone who's going to design a circuit board that has to do with a memory bus. This is the kind of timing diagram that you have to understand. So timing diagram, memory read operation. So it's really great to have Google, because now I can just look at this and go, wow, okay, I can just pick one of these to be the one that I want to use in this class. So we'll go ahead and pick. This one is kind of okay. It's this one is kind of interesting because if you look at the documentation, it says opcode fetch machine cycle of the 8085 processor. Do you think that might have something to do with the topic that we talked about in this class, the processor architecture? Yep, this is the granddaddy of the Pentium processor. So the 8085 became the 8088/6, depending on the 8 or 16-bit of the processor. And of course, that became the processor that we used in the original IBM PC XT, and then the PC XT, and basically all the subsequent processors from Intel inherit from characteristics of the 8085 processor. So this is what we call a timing diagram. And in the diagram, we can see this one is kind of unique in a way because it is sharing 8 pins. Okay, 8 pins on the processor are shared between being a part of the address bus and also the data bus. It's done so that they can save traces on a circuit board. Okay, this is back when a 3 or 4 layer board is considered kind of expensive and difficult to manufacture, or expensive to manufacture. For those of you who don't know what I'm talking about, the number of layers on it in the circuit board, what does the circuit board look like to you? When you go to Fry's, you go by the motherboard, what does it look like to you? Well, it looks like a piece of plastic, right? Okay. So if you look at a circuit board without components, it almost looks just like a piece of plastic, except it's not made out of plastic. It's made out of what usually we refer to it as FR4 material. FR4 stands for fiber. It's a kind of fiberglass. It's resin reinforced, so it's pretty hard material. Has anyone tried to break a circuit board? Yes. A printed circuit board, and were you successful? Was it a bigger board? Like about this wide?
Pretty sure I used something.
You had to use something, a hammer. You didn't break it by hand, did you? Okay, even with a bigger board where you have a lot of leverage, it's really difficult to break it by hand. You can step on one end and try to pull it and break it. It won't break. It's really, really robust. So that stuff is actually very hard. And then I hope you didn't use a circular saw, because that would not be a good idea. Okay? Because it's made out of fiberglass. What happens when you use a circular saw on fiberglass?
Dust.
You end up with a lot of
Glaze.
dust, right? Now normally when you use a circular saw on wood, you still end up with a lot of sawdust. Sawdust gets into your lung, and then what happens? A tree grows out of it. What happens?
Cancer.
Well, I mean, it's organic stuff, okay? So eventually it disappears. Your body, it doesn't harm your body that much, okay? Unless you're inhaling a lot in a short period of time. Fiberglass cannot be processed by your body, okay? You breathe it in, it stays there. It just stays there. Okay, so you don't want to use a circular saw on these things. If you ever need to break one in half or into smaller portions, the way to do it is to score, and then you break it. Okay, that approach actually works. Okay, so anyway, getting back to the circuit board thing, the number of layers has to do with, if you just look at the thickness of that thing, the simplest kind of circuit board only have traces on one side of the circuit board. They're simply called single-sided PCBs. So on one side you will see copper traces, and that's the only part that can conduct electricity. And then you can have double-sided circuit boards, right? One on the top and one on the bottom. That's pretty easy. I mean, nothing tricky to it. You just have to put copper or glue copper onto the FR4 material and use a etching process to eat away the portion that you do not need. Okay, that's usually a deletive process or removal process to remove the excess copper from the circuit board that you don't need. The simplest way to make a PCB, a printed circuit board, well, I shouldn't say printed, but it's a circuit board, is to use a Sharpie. And I'm not kidding. Some people use a Sharpie and draw out the circuit on the circuit board, and then they dunk it into corrosive solutions. And the Sharpie is resistant to the corrosive solution used to etch circuit boards. And when you're all done, you pull the circuit board back out, you clean it really good, and then you use an organic solvent to remove the Sharpie paint, and then you have your own circuit board.
Wow.
Yeah. And then if you are dealing with bigger components, through-hole components, you can even use a drill press and just drill your own holes, and then you can attach your own components onto your circuit board. So it's fun to do that, but you can only do so much with this approach, because the precision of using a Sharpie to draw out your traces is kind of limited. So a lot of components these days have such a high density that you really can't do it easily. Okay, and then if you go to Fry's, they sell special kind of things that you can glue onto the circuit board in order to make what we call the land patterns of smaller pins for smaller components. So anyway, getting back to this discussion here, if you look up a circuit board, a current circuit board, can anyone kind of guess how many layers these circuit boards have? 6 layers. Okay, 6-layer circuit board. Now, what do we mean by 6-layer circuit board? You look at the edge of the circuit board, you basically find that there's one copper at the top, one copper layer at the bottom. This is a double-sided or 2-layer circuit board, which is pretty inexpensive to manufacture, no problem. This is a 3-layer circuit board, 4, 5, 6-layer circuit board. So what happens is you have a layer of copper, a layer of FR4, another layer of copper, another layer of FR4, another layer of copper, and so on. So it becomes a big, huge sandwich of copper and FR4 material. So that's the cross section of a 6-layer board. Now, why do you think do you think this is inexpensive to manufacture a 6-layer circuit board as opposed to a 2-layer circuit board? It's way more expensive because you have to stack these things on top of each other. Okay, and each layer has its own pattern. We are not talking about a solid plate of copper. Each layer has its own traces, has its own pattern. Okay, and then on top of that, how do you get a signal, electrical signal, from the top layer to one of these layers?
Holes.
They're called vias, V-I-A, vias. So a via is used, sometimes it can be plated, and with these boards, you can have vias that only go between certain layers, not all the way through, but only between certain layers, because you just want the signal to go from this layer to this layer here. Okay, and each via is a kind of like a cylindrical conductor thing. It's usually hollow, and you have to put those inserts into the holes that you drill on the motherboard. In other words, there's a lot of process just to make a circuit board these days. But why do you think they have to go to such length to make a 6-layer circuit board for modern computers?
Question.
Yeah.
You said comment about the other one? CR?
FR4.
FR4. What is this stand for?
I think it's fiberglass resin reinforced.
Okay, and then third thing is that a conductor or insulator or what?
It's an insulator.
Insulator.
It's a very tough substance, but it's an insulator. It does not conduct. Yep. Yep. But why do we have to go through such length to
Too many
make a
traces.
6-layer circuit board? Huh?
Too many traces.
Too many traces. That's right. Okay. When you look at the memory module, that's the easiest one to actually visualize. When you buy a memory module, I think last time we counted, right? Some people said there are 240 pins on those things, right? And most
Memory board has more layers. It's
memory
like
boards even have
motherboard.
more.
Yeah, they have like 10, 12 layers.
They're 10 to 12 layers, but they're smaller in size.
Yeah.
Yep. And these are expensive to manufacture. If you look at the components on the motherboard, you think, well, the chips are expensive. But don't forget, the motherboard itself, the printed circuit board, the PCB, is also very expensive. There are other things that are expensive, and people do not think that way. USB connectors are expensive. Okay, little things that we don't really think about. Those things kind of all add up, and they're all expensive components. But the bottom line is, we need complicated circuit boards like these because there are so many traces to go from one place to another place that one layer cannot cut it, 2 layers cannot cut it, 3 cannot cut it, 4 cannot cut it, 5, and it's now up to 6 layers. Which is a lot of routing, what we call routing resources, because if you have a single layer on the circuit board and you have to route signals, okay, let's say this has to go here and this has to go here, okay, well, the first one is easy. The second one, well, not too hard. I can kind of go around like that, right? But if you have a lot of points and they cross over a lot, then at some point you cannot do it on a single layer board at all. Okay, it's just mathematically impossible. So what do? Well, if your resources is limited and you only have a few traces that you have to cross over, what people do is they put wires. They solder wires on one side of the board, and then they solder the other end of the wire onto the other part of the board. Okay, but that's very labor intensive because you're talking about soldering all these little wires by hand, on the circuit board. And that's why they move on to more layers so that they have more what we call routing resources. Routing resources refers to the ability to make a lot of connections crisscrossing and in all directions and be able to finish the routing using automated tools. Okay? How many people are thinking that you might want to become an electrical engineer or a computer engineer? Okay? So many of you will probably get to a 4-year university, and I can almost guarantee you that they won't talk about this. Okay, why? Well, because this is the job of what we call a technician. Okay, so when you work for a company that designs a circuit board, you have the engineers. The engineers come up with what we call a schematic diagram, which is just a logical connection thing. It's like, okay, this chip is connecting to this chip, and this line of this chip goes to that line of that chip, and so on and so forth. But it's all logical, okay? It's not the actual connection on the circuit board. So you give that document to what we call a technician, and the technician will use that document and figure out, how to place the components on the circuit board and how to make all these connections. Now, when you have memory chips having 240 pins, and how many pins is on the processor itself? A typical i5 chip.
More than 1,000.
1,000 something? Yeah. Okay. Well, all those pins, all those contacts have to go somewhere on the circuit board to another component, because otherwise that would not have been a pin, right?
Actually, not all. Because processor maybe half of the pins is ground.
But many of those are grounds, because you need to ensure a good ground connection. But still, even if half are grounds, you still end up with 500 plus pins that has to go somewhere else on the circuit board. Okay, the memory chips each has 240 pins. Now the memory chips do share a lot of pins. Remember, the address bus is a broadcast, signal. It's a broadcast bus, so everybody gets the same pins, as far as the address bus is concerned, and also the data bus. But we're still talking about hundreds of hundreds of connections going from here to there between the processor and the memory modules. What about the chipsets? Same thing. Lots and lots of wires going in between those also to and from your processor. So when you're talking about hundreds and upon hundreds and upon hundreds of connections, you're easily going into the thousands when you count individual logical connections. Do you think they use a person to do the what we call board layout and routing, or do you think they try to automate this process? Of course, they're going to automate this process as much as possible, right? And that's why that's why companies pay licensing fees to buy these kind of software to do all the routing, the board layout, and stuff like that. Can anyone guess how much money? What is the price of one seat, which means one person can use that software for 1 year? They are in the tens of thousands. Well, ASUS sells a lot of motherboards, okay, and defense contractor sells not a lot of motherboards, but they're expensive, right? So we are talking about so that is the kind of thing that has to go into the process when you create a new motherboard or whatever electronic that you're designing that has a lot of pins, okay? But getting back to that question, why will you, as an electrical engineer or a computer engineer, never have to deal with this, or you will not even have classes to talk about this? It's because most professors at the 4-year university level will think that this is the job of a technician, and as an engineer, you don't need to know. Now, whether you or I agree to that or not is a whole different story. But I'm just telling you that if you are interested in learning how to route a board or how to design a board, actually soldering components onto a board, you don't learn that in a 4-year university. Of course, unless I'm teaching the project class. Now, how can I say that? Because I used to teach the Micro Mouse project class over at UC Davis. I used to teach that class for more than 10 years. And in that project class, my students actually design the circuit board. They come up with a schematic capture. They actually do the layout of the circuit board itself. They route the circuit board by hand, and then they turn in the job. They get the circuit board back, and then they purchase the components. They solder the components, and then they test the whole thing. They have to finish the entire cycle of designing something. And occasionally, I have people who get burnt by a soldering iron. Just occasionally, like people who look at the soldering iron like, I wonder whether that's hot. Ow, that's hot. I mean, lead doesn't have a high melting point, but it's mighty hot when it comes to burning hands. All right. So getting back to this picture here, this digression was only because of the discussion of why do we have to share, pins between the address bus and the data bus. It's because of limited routing resources. When you only have a 2-layer board, that is already a lot of pins, a lot of traces to route. So anyway, if you look at this picture, we have the basic clock. Okay, if you look at the top part here, we have the basic clock. So this is one clock cycle. This is another clock cycle. This is another clock cycle, and so on. We have the address bus here. Okay, this is A15 to A8, which means we are dealing with bit 8 to bit 15 of a 16-bit address bus, and these pins are shared. So at this portion in T1, in time cycle T1, all 16 pins are used to specify the address. So the address is latched or is driven by the processor onto the address bus. In other words, you're telling all the chips, okay, every single memory chip, and say, okay, this is the address that I'm interested in. Okay? And then the next thing, and during this time, the ALE line is asserted. ALE stands for address something enable. I cannot remember what the L is, but anyway.
Line. Probably address line.
Address line enable? Okay, so the memory chips will basically say, oh, okay, so the address bus is now active. I better pay attention to the address bus to figure out which location the processor wants to access. Okay. And then we take a look at the other one. Whenever you see a crossover like this, it simply means that something is happening on that bus. Okay, it's not necessarily going from low to high or from high to low. It is just being changed for that particular cycle. This is IO/M, which means we are selecting between accessing IO components as opposed to memory components. This one is a read operation. So the read operation is only going to be asserted here after the address bus is asserted. And at that time, when the read signal is asserted, the memory chips will output its content, and that's why when you look at the AD7 to AD0 roll, you can see that there's a crossover here, which means this is a transition. The processor stopped driving the AD lines as an address bus, and then the memory chip starts to drive that line to output the content from the memory chip at this time. This picture does not incorporate the chip select line. The chip select line is simply not stated here. And you can see that one memory cycle takes 4 clocks, T1, T2, T3. Well, okay, 3 clocks in this case, only 3 clocks to complete one memory read cycle. That's a lot of time. That really is a lot of time. Okay, because with this one, according to the document, it's just reading the opcode or a bit of an opcode into the processor. We're not even reading the part that has to do with the number that you have to calculate. So we will need another memory cycle to read in the content that you're supposed to process. Okay, so an instruction just dealing with the memory bus can easily take up, 9 cycles? Because 3 to read in the instruction, 3 to read in a number to process. Let's say you only have 1 operand that you need to read from memory. And then 3 more to write it back into memory. So we're talking about 9 memory cycles to increment a number that is in memory. And that's not even counting the amount of time the ALU requires to do the actual processing, which is at least 1 clock. So we are talking about 10 clocks just to do one single instruction. Now, if processors are still like this, that means your 3.5 gigahertz processor can really only do 350 million instructions per second, because it takes 10 clocks to execute one instruction. Is that making any sense? But that's really not the case. We use, modern processors make use of, special techniques. Pipelining is one of those techniques, so that they can stack instructions. So in other words, you can be doing phase 1 of one instruction, but the other part of the processor would be processing phase 2 of another instruction. It's kind of like in a plant, okay? In a manufacturing plant, they use the flow, they use the pipelining flow to improve the throughput of, assembling something. So let's say we're assembling a Furby, okay? And to assemble a Furby, there are 4 steps. So what used to happen is the same person will be responsible for all 4 steps of assembling a Furby. Okay? Pipelining basically says, okay, I'm only responsible for the first step of assembling a Furby. Okay, so I'll get the circuit board ready. I'll get the stuff for the soft part ready. I'll get the skin ready, and then I'll move the half assembled Furby to the next person. So the next person will say, okay, I'm only responsible to put the stuffing into the Furby. I will be responsible to put the battery into the battery holder, and so on. Okay, and then the third person will do something else, And then the fourth person, maybe the last one, will put everything together, including the tag, and put it into a box, and it'll be ready. So this is called pipelining because each person is only responsible for one step. And the partially done product is passed on to the second person, the third person, and the fourth person. So now your throughput becomes 4 times the original throughput, right? So pipelining is one technique. But some people would argue and say, well, instead of pipelining, why don't we have the 4 people, each person, to complete the entire 4 steps of assembling a Furby? There's nothing wrong with that, right? Well, there's absolutely nothing wrong with that. That's having multiple cores. Okay, it's equivalent of having multiple cores in a processor because they're all kind of independent, right? Each core can be doing something entirely differently and independently from the other cores. So we do employ all of these techniques to boost the throughput of a modern processor. And that's why we are not observing this kind of, 10 clocks for one instruction and more. Instead, we are now observing multiple operations per clock because there's a lot of parallel processing inside the processor going on. And that's also why the memory bus becomes a big problem because you cannot feed the processing elements fast enough in most cases inside a modern processor. And I think that's also partially why, beyond having 4 cores per chip doesn't make a whole lot of sense anymore. What if you can theoretically put 16 cores onto the same chip? What would that buy you? Lots of virtual machines. But you have to feed those 16 cores.
A good heater.
A good heater. It won't even be heating up much because the lazy cores or the cores that are not doing anything, they don't even need to do anything. It's not even consuming a whole lot of power when they don't have anything to process. So that's why there's a practical limit of what makes sense because you can put as many cores as you want onto the same die, okay? But can you keep all of the cores busy? That's the big question.
Well, they don't have software for it yet, but who knows?
The software part is a big deal. You're absolutely right. They don't have software to utilize multiple cores. A lot of operating systems, are natively capable of making use of as many processor cores as possible. Like in Linux, okay? In Linux, you can, I know you guys know that I use Linux a lot, but Windows came really late to the game. When was the last year that your Windows game could not utilize a quad-core processor? It wasn't that far in the past, right? The quad-core processor came out before the games were ready.
Same thing with HexCore, because they have HexCore. You can get them, but nobody buys them.
Because no software is utilizing those resources. Exactly. Yep, go ahead.
So one core is basically the compiler already optimizing on that. So if you write something in C or optimize on that one core parallel processing, then you have to run stock threads.
That is correct, but the processor also does a lot of tricks even on a single core. If you look at a single core, even without hyper-threading, the processor actually, when it's doing pipelining, sometimes it will reorder the order of instructions. In other words, it will read in the instructions and it will try to figure out the interdependencies of the instructions. And then in real time, on the fly, it will try to reschedule things without impacting the end result, but try to utilize as many of the ALUs on the chip as possible. And all of that stuff is without compiler support. The compiler is just spewing out instructions as if there's only one core and one ALU doing everything. And inside the core, inside the processor, they use silicon to analyze the stream of instructions and try to tweak everything to make use of as many resources as many resources as possible inside the processor core. So what you see here is really, just for instruction purposes. It has no resemblance to anything that a modern processor actually does. But it forms a good basis, of understanding how it works. So are there any questions, any comments? Yep.
How do they deal with the memory bandwidth like in a graphics processor then, where there's several hundred
cores?
Okay, that's a different story because with a graphical processor, they don't have the same problem that we have with general purpose programming. Okay, when you have let's take a look at a graphics card. Okay, so a graphics card with hundreds of cores with a high-end card, they all perform processing to the screen, but they can segment the memory access also, because they're working. Well, for one thing, they're working in parallel. Okay, and for the other thing, ray tracing and most of the algorithms used actually scale really well with the number of processors. But in terms of memory bandwidth, they still have a problem with memory bandwidth, except they're designed to do things a little bit differently.
So is it like the different cores access different areas of memory simultaneously?
No, they still have one bus. So it depends on how many buses they have, and the more buses they have, the more things can go on at the same time. Now, since we're talking about having multiple buses and customizing design to make the throughput improve, there's one easy design to improve this whole situation. The von Neumann architecture is basically saying your data is residing in the same memory as your instructions. Your opcode is coming from the same book, basically, as the data. And that's why it becomes a bandwidth limitation, because you have to read the instruction from memory, but whatever data you're processing is reading from the same chunk of memory using the same bus. So you have bus contention all day long because of that. Now there's a different modified architecture called the Harvard architecture. Has anyone heard of the Harvard architecture? The Harvard architecture is slightly different, but it makes all the differences. It basically says we have one bus, one pair of buses, okay, a data bus and an address bus for instruction, and a different pair of buses for data. So now there's no contention, because to fetch your data, you'll be using one bus, but to process, to get data or to store data, you're using the other bus. And just because of that, they can improve the throughput quite a bit, just doing that. The Harvard architecture is typically not used with a design where the processor is separate from its memory banks, but it is used more often when you have memory and the processor on the same chip, on the same die. Okay, the Atmel AVR processor falls into this category, where instruction comes from one bus pair and then data comes from the other bus pair. And it really greatly improved the efficiency without having to increase the die size a whole lot. So these are all kind of fun things to talk about, all the optimization that people have done to the basic von Neumann architecture. So I'm just hoping that you guys are just getting an exposure of what a timing diagram looks like. When you see a line like this, it means a trigger. So this edge from the read line is triggering the memory chip to latch out or output or drive the data bus. So the opcode is now presented on the data bus. This rising edge of the read line is triggering the memory chip to release the data bus and say, okay, I think you got it. I'm going to stop driving the data bus. Okay, and here's one other thing that I just want to point out is this is a read operation. So how come the read line going low is actually causing this to happen? This is called an inverted, well, not inverted logic. It's called an active low signal. Active low means when the signal is low in terms of voltage, it is asserting that operation. Okay, because normally we think when a voltage is high on the line, it is asserting that function or whatever function that pin has meaning for. But in some cases it is inverted. So in this case it is inverted. You can see from the bar on top of RD, that means it is an active low signal. When the signal is high, when you use a voltmeter, it is high, it means it is not asserted, it is not reading. When it's low, it is then actually reading. It's called an active low signal. And active low has a lot to do with the type of transistor we use in the processor, which typically are the N-type, or NPN in the good old days, but now it's called the N MOSFET. But because of the substrate, and it's the less expensive of the two, because you can have an N type or a P type. The N type is the less expensive one, and it lends itself to active low signals. So that's partially why we have that sort of thing.
The N-type you're meaning by NP and NPN meaning PNP, right?
NPN is also of the same type, because it's an N-type transistor. But when you move on to MOSFETs, they also have N-type MOSFETs as opposed to P-type MOSFETs. MOSFET stands for metal oxide semiconductor field effect transistor. And I'm just a software guy. Don't ask me anything about device physics. I know nothing about that.
You just told me something right now.
So anyway, just an exposure to timing diagrams, and we can kind of go back to here. Okay, let's go talk about accessing I/O, because we have been focusing a lot on memory. Okay, what do you do with a computer system? We are not just talking about the single chip or the processor. What do you do with a computer system that has a processor, memory, and that's it? Okay, computer, turn it on, and it definitely has some output, right? in the form of hot air, yes. Okay, so that means input output is also important. Okay, with a modern computer, and I'll just go ahead and give you a prop of a modern computer. So with a modern computer, yes, it is a computer pretending to be a phone, right? Okay, so on a modern computer, what are the input-output devices? This one has a lot, right? It has got, we can see the touch screen, we can see the camera, both sides of the camera. We can see the microphone, USB, gyroscope, or accelerometer.
Bluetooth, Wi-Fi. Bluetooth, Wi-Fi.
Okay, Bluetooth, Wi-Fi, near-field communication. Some have IR capability. They can also use IR.
That's gone.
That's gone. You don't use IR anymore. So I can't use my phone to remotely control my TV anymore.
You can. With the app for that now and everything. Not really like that.
Yeah, I have my
For some reason, some meters.
Okay. Oh, but don't forget the LED. My trusty flashlight, right? Turning a $200 device into just a flashlight. Okay, now I can see in the dark. All right, cool. But those are all I/O devices. Okay, input output devices. And we have not talked about how a processor can talk to I/O devices. We have only talked about how the processor can talk to memory. And memory is completely inside the system. You cannot observe memory. You cannot observe the state of memory. That's just it's just not designed for that sort of thing. So we need to somehow talk to input-output devices. And what do you think output-input devices look like from the perspective of software?
Ports.
They're basically ports. Okay. So just like memory, the I/O space has locations, has addresses. Okay, so there's location 0, location 1, location 2, and all the way up. But each location does not correspond to memory anymore. When you write to an I/O location, you are not going to store that content at some location in memory. What are you actually doing when you write to an I/O location? You are talking to a particular I/O input-output device. Now that input-output device can be your USB device, can be your Wi-Fi device, and so on and so forth. Now, depending on which location of which device you're talking to, the function of each bit can be different. Okay, so with one bit, you can be saying, do we want to turn on the, let's say, power saving feature of your Wi-Fi chip? Okay, and so on and so forth. Some locations are also special. When you write to those locations, you will actually be generating an output from a certain device. Like in the good old days of serial communication, there's a data register associated with a serial communication chip. So when you write to that location, then the logic or the circuitry will actually clock out the ones and the zeros onto the serial bus. So otherwise known as RS-232 communication. So that's how a program can talk to I/O devices. And there are other I/O devices that we don't even see inside a regular computer. What about your hard drives? Well, it's an I/O device. Okay. What about, well, USB is one, and then your gigabit network card is another one. So there are tons of I/O devices, and they're all accessed through I/O instructions. Now, there are two types of methods to get to I/O devices. The first one is what we call memory mapped I/O. Now, this is a kind of tricky one because what happens is in the earlier days when Apple still used the 68,000 processors, the 68,000 processor has no specific instructions to do with input-output specifically. In other words, as far as the processor is concerned, it only knows how to read and write memory. Okay? But that's not a problem, because what people have done with those processors is they will reserve a certain range of addresses in the memory space and say, okay, you know what? These addresses do not actually correspond to locations in RAM. They actually correspond to registers or I/O registers on the I/O devices. So when you write to a certain memory location, you're no longer dealing with RAM or ROM. You are actually dealing with an I/O device. So as a result, it is called memory mapped I/O. It's typically done to non-Intel processors because the 8085 ancestry of the Intel processor line already has specialized I/O instructions to do with I/O devices. So this is typically applied to PowerPC. I'm not sure about the PowerPC, but I know for sure the 68,000 processor family does not have I/O instructions, and then as a result, they use memory mapped I/O in those cases. The next slide applies to the i386 or the entire family of 8085 derived processors. They have specialized instructions to only deal with input-output. In other words, when you want to talk to your USB devices, you are not going to use the same instructions that you would normally use to address memory. So the instruction to read from memory is actually different from the instruction to read from an I/O device. And as a result, the input-output locations have what we call a different space because it has its own location 0, its own location 1, its own location 2, and so on. And then your memory has a separate location 0, 1, 2, 3, 4, and 5, and so on. And they are not, there's no correlation between the two spaces.
So the actual code that you're sending, the instruction like the code that you're sending, the actual memory, that's different.
Correct. The opcode is different. When you want to write to memory location 0, that instruction is different from the instruction to write to memory to write to I/O location 0. So they're entirely different instructions. And the Intel architecture uses I/O map instructions. Are there any questions about memory mapped I/O versus I/O mapped I/O? It's a specific bus basically designed just for input-output devices. When we go back, well, I closed that page already, but if you remember, the previous picture, it also has one line that says, IO/M. And that's the selection between, are we talking to I/O devices or are we talking to memory? That's the one signal line that makes the difference. Who am I talking to? Memory or input-output devices? So are there any questions about how a computer talks to I/O devices? No? Okay. If there are no questions, then we'll go ahead and move up. And we talk about cache a little bit here. We talked about burst mode memory access, which we talked about in the previous class already, regarding basically DDR type of memory access. We didn't really spend a whole lot of time on cache, so we'll go ahead and go through this slide, just really kind of briefly. A cache is a special type of memory that sits between the processor and memory. Logically, that's how the location of it. So if you remember the analogy, if I'm the processor in this room, memory would be content that is in the library. Okay, it's really far away. It takes a long time to get there and come back here. Okay, And I can do processing a whole lot faster than you guys can run back and forth the library. So what do? Well, we have the concept of a cache. In the past, or in the distant past, cache is not on the same die as the processor itself. It is actually external to the processor. But these days, we also incorporate cache onto the same die as the processor. But it is still not a part of the ALU. It's not a part of the control unit. It is a separate part of the processor. What cache is doing is cache is what we call associative memory instead of regular memory. So the way it works is, we basically just imagine that outside this room here, we have, let's say, 5 binders, okay? And on those 5 binders, someone can keep track of the most frequently accessed pages that I want to use in the library, okay? So somebody's going to figure out, oh, tech always wants to refer to chapter 10, the second page of chapter 10 of this book, okay? Somebody figures it out, not me, not the processor. So the cache controller is something that is independent to the processor. So somebody figures that out and go like, well, since he's always going to refer to that page, I'm going to keep a copy of that page in this binder right outside of the classroom. Are we doing okay so far? Now, how can we keep track of that page and say, when I scream out and say, I want, I want the second page of chapter 10 of this book, okay? And I ask one of you to go out, to get that page for me, okay? So what do? When you run outside of the classroom, you immediately go to the binder, okay? And then what you do on the binder is you use what we call the associative memory, access, and you try to look up, is there a page in this binder corresponding to page 2 of chapter 10 of this book? Okay? And if you find it, hey, you know what? You don't have to run all the way to the library anymore. Okay? You just grab that page, outside of in the binder, outside of the classroom, and you come back in and say, okay, here's the page. That's the function of a cache, is to so that you don't have to make so many trips to the library. Are we doing okay so far with that analogy? Okay. So obviously, the bigger the binder we have, the more content we can cache, the better. So why don't we have gigabytes upon gigabytes of cache?
No space.
Then it becomes the memory. You understand the memory.
But why not? But why not? That's the question.
No
It's
space
because
is
of
cheap.
silicon. It takes a lot of silicon to implement cache memory. Because once again,
Biggest part of CPU is cache.
Yep. If you look at the
Area.
processor die, but that's the portion that looks regular. Everything is easy. There's regularity. When you look at the actual processor part, it's irregular. There's all kinds of random stuff, well, quote unquote random stuff going on. Okay. But there's a limitation of how much cache we can fit within the die, on the same die as the processor. But why don't we make cache external to the processor then? Then we can have additional chips to implement cache just like the good old days. What is the downside of that approach? It would be much slower, because now you have to run longer traces to the cache. And remember what a trace is. It's a capacitor, it's a resistor, it's an inductor. The longer the trace, the more effect it will have in degrading the signal, and the slower you have to, the more you have to slow down to make sure that you're reading the correct information from that device. So we don't want the cache to be sitting too far away from the processor, because the further it goes, the slower it becomes. Okay, it's not because of the device itself; it's just because of the distance. Okay, so that's why we put cache on the same die these days, just to make it more efficient. Okay. Sorry.
Just make the die smaller, right?
Yep, we try to make the transistor smaller so that we can fit more stuff within a smaller space, and as a result, we can turn up the clock speed, because now the effect of the inductor and the capacitor will be less. But there's only so much we can do, because when you reduce transistors down to a certain size, which is the current size, or not very far from the current size, what do we start to see? Sorry? Well, dropping power is good. Okay, improving performance is good, but we're running up against a physical limitation. Say again? Yep. because when the CMOS, okay, when we talk about MOS, MOS, which stands for metal oxide semiconductor, the metal oxide is intended as a insulator. Okay, it's intended as an insulator because for field effect transistors to work, you need an insulator between the layers. So you can kind of imagine that there's an insulator layer here, and then there's semiconductor down here, and a conductor up there. Okay, so this is supposed to be not conducting electricity between these two layers. Okay, when we make transistors smaller and smaller and try to improve the response speed of a transistor, the faster it can switch, the better. We try to reduce the thickness of the insulator layer. Okay, and we are down to the thickness where an electron can jump across the barrier and just appears onto the other side because of quantum effects. And so that's it, right? If an electron can escape because of quantum effects, then we cannot reduce the thickness any further because it is no longer an insulator as far as this electron is concerned. Yep, we are running up against this kind of limit. Yep. So it's all kind of interesting, and I'm not making any pretense that I know anything about quantum physics. This is just what I have learned from reading literatures. And I'm pretty sure someone in this class will learn a lot more about quantum physics because you want to learn more about quantum physics. It's interesting stuff. Von Neumann himself is actually a quantum physicist too. So that's an interesting thing because he actually applied a lot of theory that he learned from quantum physics to computers. Okay, just go ahead and read his bio. Okay, read his bio, and you will find that he uses a lot of. He's the first one who came up with the concept of a stochastic machine, a stochastic computer, where things does not have to be deterministic. In fact, the more random, the better. Okay, so you might want to read up on that because it's a really interesting idea of doing computation in a noisy environment. Okay, what if things are not discrete? Any questions? Okay, so what if you're dealing with a noisy situation where things are not discrete? You can no longer trust, when I see a 0 on this line, does the other side really mean to transmit a 0 to me? Maybe, maybe not. Okay, so you have to read up on von Neumann on stochastic machines because he actually has some really good idea on that sort of computing. All right, so we are almost done with this module. So I'm just going to go through all of these just to make sure. Memory chip. So this one actually goes through all the detail to explain, what are the components inside the memory chip. And go back. Memory system, logical memory space. Logical memory space, basically just have to do with what a software person is dealing with. In other words, remember last time we had 4 memory chips to implement or to supply the 1,024 locations. Each chip has 1,024 locations. So between the 4 of those, we have 4,096 locations. Remember that? Okay. But from the software perspective, you don't even need to know that. Okay. We can be using one single chip with 4 kilobytes. We can be using 4 memory chips, each one with 1 kilobyte. By the time it gets to the software specification, it all becomes a linear space. It becomes a logical space, so you don't have to worry about, which chip select line am I supposed to assert to get to the right bank of memory. That's all done in hardware. It's typically done by a subcomponent of the processor called the MMU, okay, the Memory Management Unit, which has a lot of other things to deal with, because all the processors can also do virtual memory, and that's also a part of the MMU, which is kind of like a big component inside the processor. All right, so now that we are done with this, I'm going to switch back to Johnny. So what we'll do with Johnny today is we're going to single step through a single instruction. So we'll pick one single instruction, write a very simple program with one single instruction, and then we'll try to figure out, okay, what exactly is it doing when it executes that instruction. Is that okay? All right. So let's go ahead and write the simplest program that we can possibly write that is still doing something that is interesting. Okay. So the way you write a program with Johnny is just click on a memory location. And the good thing is we don't have a whole lot of actual physical switches to deal with. We're just going to specify a number here. The high part of a location specifies the opcode. In other words, this is the part that specifies what the instruction does. And we're going to do something not very exciting. We'll use the null instruction. The null instruction, as the name implies, doesn't do a single thing. It's just sitting there, taking up space, but it doesn't do a single thing. Okay? But that's okay. We can deal with that. Because it's a good example of what is the minimum number of things in order for an instruction to do, just to get to the next instruction. All right? So it doesn't require an operand. The operand part is actually ignored. So now I have just programmed the first location. And then the second location, I'll do another rather simple instruction. Doesn't do any type of processing. It's the jump instruction. Okay, so we have the JMP instruction here. And now with a jump instruction, the low portion of a memory location becomes useful because I have to tell it where we are going. Okay, where am I going to continue execution? And in this case, I am intentionally trying to make an infinite loop. So I'm jumping back to location 0, where the null instruction is. The null instruction finishes its operation, which is nothing, and then we move on to the jump instruction, and then moves back to the 0 location, and so on. Okay. So these are the two instructions of this really simple program, but even though it's simple, it never ends, right? Okay. So now we have this rather tiny little program, doesn't do anything really useful. If you run the program using this key here, you have just missed the entire point of this program. Unless you are cold and you want your computer to warm you up. Okay? Because this is an infinite loop. We already know it's an infinite loop. So the whole idea of this program is not to single step through the macro instructions, but to single step through the micro code of the instructions. Okay? So let's go ahead and single step through the micro code of the instruction, which is done by this little key here, this little button here. Okay? Now, before we even single step through it, we can actually predict what is going to happen next. How can we tell what is going to happen next in terms of microcode, following the microcode of this thing? It's all down here, isn't it? So the highlighted portion is basically what we are doing. These 4 microcode steps collectively is called the fetch cycle of a processor. These 4 microcode is responsible to read the next instruction that we are supposed to execute. Okay, so let's go ahead and take a look at these 4, and then we'll go ahead and trace it. The first one says PC to AB, which is program counter to address bus. PC to AB also matches this label here, so its only job is to take whatever you have in the program counter, which is currently is 000, and output that onto the address bus. In other words, the processor is now driving the address bus and say, I want something from location 0, or I want to do something with location 0, whether it's a read or write operation is specified in another step. So at this point, it's just saying, I need to access location 0. Okay? So let's go ahead and single step this one. You can see this is highlighted to mean that now it has the content of 000. The second microcode step specifies RAM to DB. RAM to DB means once we have the address bus driven by the processor, the memory portion, the RAM portion, now knows which location is being addressed. Okay. Oh, I can see that you need to access location 000. That's what the RAM portion is saying right now. But when we activate RAM to DB, which is the current operation or the pending operation to happen, we are basically saying, okay, get the content from memory, which at this point is 09000 because that's the content of location 0. We are basically saying, use this content to drive the data bus. So the data bus itself has the content of the memory location that we are trying to address, or we're trying to access. Is that okay? Okay. So now we single step through RAM to DB. Okay, we are single stepping through this. I'm not pressing the button here. I'm just single stepping here. And sure enough, this is the content of location 0. And now the data bus also is specifying that content, because at this point, the RAM portion of the RAM module is driving the data bus. In other words, the RAM portion is specifying the content on the data bus. The data bus is nothing more than a whole bunch of wires in reality. So it cannot really store its own content. It can only be, it's just a conductor. So something has to be driving the bus in order to have content or meaningful content on the bus. So what happens when the bus is not driven? It crashes, right? A real bus. I'm not quite as good as Larry in terms of doing this sort of thing, but I'm learning. I'm getting there. All right. So the next step here is called DB to INS. Okay, it's from data bus to instruction register. Now, if you just look at the picture and know where the instruction register is, you can quickly locate, oh, this path is going to be activated. In other words, at this time, RAM is still driving the data bus, and as a result, the data bus has the content of the location that we are trying to access. But this operation here is going to read whatever content is specified by RAM and put it into the instruction register. Are we still doing okay so far with these steps? Okay, so I'm going to single step through this microcode here, and this activates, and sure enough, the instruction register now becomes 09000, which is reflecting the content of memory location 000. In other words, we have just read an instruction from memory, from RAM, into the instruction register. All right? Are we still doing okay so far? So our fetch cycle is almost done. In fact, we are almost done, because the next one, the only microcode remaining to execute is instruction to microcode, which is this little icon here. And what it does is, you can look at this as an array index operation. Okay, it's taking a look at the the high portion of the instruction register, which is 09, and is using that as an index to index into the microcode library to location 90. In other words, we are reserving 10 microcode steps per instruction. And because the instruction is 09, the microcode corresponding to this instruction is starting at location 90. Are we still doing okay so far? So that's just a really indexing operation. You're multiplying the number by 10 to go to the location where the microcode is going to start. So microcode execute, one more step, and sure enough, now we are at location 90, which has a comment or annotation that says this is the beginning of the null instruction in terms of microcode. All right. So the first thing we have to do here is to execute INS to AB, or instruction register to address bus, which means we are taking the low portion here, 000, into the address bus here. So we'll go ahead and execute it. And now the address bus has 000. It had 000 before. And then the next step is ACC gets 0. ACC gets 0 means the accumulator, whatever content it had before, doesn't matter. We're going to reset it back to 0. Well, since it's already 0, it's not going to be observable, but nonetheless, that's what we'll do in the next step here. ACC to DB, accumulator to the data bus. So we're going to latch this back onto the data bus here. So this line will be activated. So we will basically use the accumulator to drive the data bus. So now it's the processor's turn to drive the data bus. Single step. And you can see the data bus is now, has now changed its content to 00000. And now we're going to go from DB to RAM. Ooh, that's not going to be good. Okay. That is not expected. I did not think the null instruction is going to do this. I thought
Just unificate.
it's no in the memory location. Okay, I did not. I was not anticipating this. I thought the null instruction is a no op, but it's not a no-op instruction. Let's find out what's going to do next. I think most of you already know what it's going to do, right? Okay, because it's a DB to RAM operation. DB to RAM here, which means I'll take whatever content is specified on the data bus and use that to overwrite the location that is being addressed, which is this location. So let's go ahead and do it, and then we'll say, wow, that's not such a good idea. And what just happened? I have just done something that is called self-modifying code. The program is modifying itself. Not intentionally, okay? In your homework assignment, it was intentional. With this one, it was not, okay? But, it's still okay because, we still have the next instruction to execute, okay? The next one in the microcode is PC++. PC++ is here. So what it's going to do is just to increment the program counter by 1. So you go from 000 to 001. All right, well, that's okay. We can do that. Single step. 000 becomes 001, and we're going to reset the microcode counter back to 0. Now, if you reset the microcode counter back to 0, where are we going back to?
Fetch.
All the way back to the beginning, the fetch cycle, right? So we'll go ahead and single step through that thing, and now it is back to location 000, and well, we are not in trouble just yet, okay? Because the program counter is incremented to 001. So we have a fresh instruction to execute now. Okay. So we go through the same for cycle, PC to AB, which means the program counter goes to the address bus to specify which location I want to access. Single step. RAM to DB. Now we want to read from memory. So we should read this 05000 onto the data bus at this point. DB to instruction. So the data bus content is going to overwrite the instruction register. And finally, instruction register to microcode. So we'll decode the 05 and index to location 50 to start the microcode corresponding to the jump instruction. And now we're at the beginning of executing the jump instruction in terms of the microcode. The first thing it does is INS to PC, which means it is performing this step here, is taking the lowest portion or the low portion of the instruction register and copy that to the program counter. In other words, I am just hard coding the location of the next instruction, which is location 000. And that's it. The jump instruction is a very simple operation because all we're going to do is to say, oh, okay, we'll just copy the operand, which is the 000 of that instruction, over to the program counter because I'm just changing the program counter. That's going to change the instruction, the next instruction that I'm going to execute. Single step. We go back to the beginning part of the fetch cycle, and now we're in trouble. Okay. Well, it's not trouble. In fact, I would call this is the simplest infinite loop ever.
Yeah.
Okay, now let's go ahead and see whether it is an infinite loop or not. Because when we execute PC to AB, okay, let's go ahead and execute PC to AB, which is going to copy the program counter onto the address bus. Okay, now we specify location 000, the content of that location is 00000. We read from memory into the data bus. We are asking the RAM module to drive that content onto the data bus. And then from DB to instruction register, in other words, we are reading from the data bus and use that content to overwrite the instruction register. So now the instruction register becomes 00000. And then we use this instruction here, INS to MC. What do you think INS to MC is going to do?
Going to start over
It has the same,
microcode.
exactly, it has the same effect as MC : 0. Because what is the instruction? What is the high portion of the instruction register right now? 0. Okay, how do we find the beginning of the microcode corresponding to the instruction output 0. Multiply that by 10, right? What is 0 times 10?
0, bro.
location 0. So it's going to do this all over again. Did I change the program counter at all?
No.
No. Okay, so that's why this is an infinite loop without using the jump instruction.
So if you have 0 in the fetch, then it's going to stay 0 no matter what.
Say again?
If you have 0 in the fetch, then it's going to stay 0, right?
If I have a 0,
Like fetch.
the fetch cycle itself is instruction opcode 0. Yep.
Then it stays 0.
Yep. So with the other instructions, this is also something that you can do to find out what the instruction does, okay? But at a microcode level. So let's try something else, okay? Just so that it is more interesting. So let's pick another instruction that we're gonna do here. I'm gonna pick one that is also in your mystery program called INC, which stands for increment. Okay, this one is a little bit more interesting, so we're gonna pick this one here. So I'm gonna overwrite the memory here, reset memory back to the beginning, and we'll also go ahead and reset the microcode counter. So now everything is reset back to this location here. Okay. Well, we'll go ahead and find out what this one does. Okay, this one is kind of interesting too. With this one, if you run it in macro mode, it will still be doing something that is observable. So you can also do that. But since the whole idea of this is to look at things from the microcode perspective, let's go ahead and do the microcode instead of the macro code. The first part here I can kind of zip through because it's just going to read this instruction in and try to decode it. Okay, so I'm going to zip through the first 4 steps until we get to the microcode of the increment instruction itself, which is right here. Now we are into the microcode for the increment instruction itself. The first thing it does is to 0 the accumulator. In other words, if the accumulator has some other content, it will now be reset to 0. Since it's already 0, we cannot really observe the change. The next instruction is instruction to address bus. It takes the low portion of the instruction register and use it to specify the address bus. The next one is RAM to DB. It takes the content of RAM at that location and use it to drive the data bus. So now the data bus has the instruction itself, and then it uses a plus. Now the plus operation is not really well documented, and what it does is it's going to take whatever is specified on the data bus, add it to the add that to the accumulator, and store the result in the accumulator. In other words, the other way to say this is to use the content specified by the data bus and add it to the current content or value of the accumulator. Yep.
Why don't you use the data bus to accumulator instead of using the plus?
That's a good question because it would accomplish exactly the same thing without having to 0 the content first. If I just doing a DB to accumulate, that's a good question. Yeah, but it would have accomplished the same thing. No, but if you use DB to accumulator, that will overwrite whatever content that we have in the accumulator automatically. Yep.
So if the high portion is 07, is that like 7,000?
No, 07 in this case, well, it's a different portion. So the high portion is used to specify the opcode of what operation we want to perform. The low portion is used to specify, well, do we need any additional information for that instruction to execute? Well, in this case, yes, because I need to know which location is getting incremented, and it's location 0.
So the plus thing, it adds the high portion to the amount of the accumulator, and so that's added on to the accumulator, for example. Is it going to show it?
Well, let's find out. Okay, let's find out what plus is going to do. Because plus is going to take whatever content we have on the data bus, has nothing to do with the instruction register. Okay, it takes whatever. If you just follow the green line here, okay, that reminds me of
Wizard of Oz?
yes, the Wizard of Oz. Okay, I'll stop there because otherwise it will be a long digression again. So we take whatever content is on the green data bus, and we'll go through this operation called plus, which takes the content of the data bus add it to the content of the accumulator, and then store the result back into the accumulator. Okay. And sure enough, the accumulator is now 07000 because it was 0 before. The next instruction is add 1 to the accumulator increment. So it will go from 07000 to 07001. Okay, let's just double check. Yep, exactly what it's doing. This operation specifies accumulator to databus. In other words, it will take whatever value we have in the accumulator and use that to drive the databus. So now the databus will be driven to 07001 because that's the content in the accumulator. And then the next step is DB to RAM, which means we are writing back into RAM using the content on the databus. So this value will now be used to overwrite this location because we are still addressing location 000, but we're specifying the new content to be 07001. And as a result, we have a self-modifying program again. Are we doing okay so far? This program is interesting. Well, but when we get to that part, you will know. Okay, it's going to do something that's kind of interesting. And then we'll increment to PC++. PC++ is just adding 1 to the program counter. So the program counter is now 001, but we are not reading that content yet because the program counter is internal to the processor. Until we activate PC to AB, it doesn't get out onto the address bus. Single step again, it goes all the way back to the fetch cycle. So now we are ready to fetch the instruction at location 001. We latch out the address bus. Now we know that we want to access location 001, but at this point, nobody has said anything about it. Is this a read operation or a write operation? We're just saying, oh, I'm interested in location 001 in RAM, but I'm not specifying, am I writing to it or am I reading from it? The next microcode does is RAM to DB, so it's a read operation. And then we have DB to INS, which means take this content and use it to overwrite the instruction register. And the instruction register is now overwritten to 05000. And then we want to decode the instruction, which means take this 05 here, multiply it by 10 so that we can locate the location of the next microcode instruction. And so we continue at location 50, which is the jump instruction. We talked about this already. We take the we take the low portion of the instruction register, copy that to the program counter. So now the program counter is reset back to 0, and then we reset the MC counter or the microcode counter back to location 0. So we are going back to location 0 to perform this operation. Now this operation is going to do something funny. Okay, so without actually microcode stepping the entire thing, what is this instruction going to do?
Jump. Is it going to increase the low and jump?
Exactly. It's going to increase the low of jump. So jump will now point to itself. So, all right. So let's take a look here. Okay, this is going to be interesting because now I'm decoding the instruction. RAM to DB. DB to instruction, so that we have the actual jump instruction, the increment instruction loaded into the instruction register. And now we'll execute the increment instruction again. So you might think, well, we have done this already, it's no fun, it's really just incrementing the value of a location. But the question is, which location is it incrementing this time? It's not the one from before, because the program self-modified itself. Okay, so let's go ahead and take a look at what it's going to do this time. Okay, accumulator is zeroed. The instruction to address bus, we want to access location 001, not 000 anymore. RAM to DB, we use the content of that location to drive the data bus. And we want to add 1 to 05000 to the accumulator. So the end result is the accumulator just getting that value, and then we increment the accumulator so it becomes 05001. and then we use ACC to DB to write it back into the memory bus, and then we use DB to RAM to write it back into memory. What just changed? Not the first instruction.
Jumps off.
The jump instruction itself got modified. Okay? And according to that instruction, what do you think that jump instruction is going?
So it's out.
To itself. Yep. So we just made an infinite loop a tighter infinite loop, because now instead of having 2 instructions in the infinite loop, it has 1 instruction in the infinite loop. Well, let's double check to make sure that that's exactly what it's going to do, right? Now we are going to read the instruction of location 1. So we'll just kind of fast track through the first 4 steps. And now we are ready to decode the instruction to location 50. Okay, you can see the program counter did not change. Reset the microcode counter back to 0. Now we're back to here. We're going to read from the same location, load the same opcode into the instruction register, and execute the microcode of the very same instruction as the previous one. So now we are stuck. Okay? So the first time you look at this program, you think it's an infinite loop, didn't you? You already know because, oh, okay, location 0 is doing something, but location 2, excuse me, I take it back. Location 0 is doing something, seems like kind of not so important. And then location 1 is going back to location 0. Oh, okay, that's a loop. We'll just be executing these 2 instructions infinitely, right? Not quite, because the first instruction modified the second instruction. As a result, the second instruction becomes its own infinite loop because it's jumping back to itself. Okay. But I'm just hoping that this exercise kind of let you take a closer look at how an instruction executes and what are the things that microcode can specify. Okay. So when you have a question about, okay, I'm running up against the wall in my homework assignment, I don't know what this instruction is supposed to do. Write a 2 or 1 line program in Johnny, microcode through the whole thing, then you will figure out what it is supposed to do. All right, so this is the end of today's lecture. And fortunately, this class is on Tuesday next week, so we don't have a break. But have a nice long weekend and happy Valentine's Day. I don't really know why people say happy Valentine's Day, because Saint Valentine actually died a fairly horrible death. There's nothing romantic about his death. Right?